Hello Earth Science students, welcome back to another one of my videos. Today we're going to continue what we were talking about last time with ocean currents, and we're going to talk about two very important aspects of ocean currents and how these two things affect ocean currents and affect other things on our Earth. Those two things being the Coriolis effect and Ekman spirals. Now, before we get into it, I have to warn you, there are a lot of extra videos that I need you to watch. This video is hopefully going to be relatively short because of that, but the reason I have to have you do that is because typically during this time we do a lot of hands-on labs that obviously we're not going to be able to have the chance to do. And so what I'm hoping to do is give you some videos of like how those things would work. For example, there's a video on upwelling that usually I demonstrate in class. There's a thing with Coriolis effect where we actually put a globe together and spin and we drop droplets of water and we can see how the Coriolis effect works. I have to do a video of that now instead of actually doing it with you. But please, please, please make sure that you watch all of the short videos I post after this one because they will greatly help you out and you're going to need them to do some of the assignments. But without further ado, let's get into Coriolis effect. So what we need to start with is Newton's first law of motion. I'm not even going to try to do the Latin or pronounce any of those words, but what you need to know about Newton's first law of motion is an object at rest will remain at rest, and an object in motion will remain in motion unless acted on by an external and unbalanced force. Okay, so basically what we're saying here is that things are stationary or they continue to move unless some kind of force is applied to that thing. This has to do with the Coriolis effect because basically what's going to be happening is things are going to be acting on our water and our currents that cause them to do certain things. Okay, so this is a slide to remind you that you need to watch this video of these two MIT professors. What happens is they spin around in a circle, and this rotation is meant to simulate the rotation of the Earth. And what they try to do is they try to pass a ball back and forth, and what ends up happening is actually very unusual. They seem to be throwing it straight, but it appears to curve. But that is only due to the rotation of the people, not the ball actually curving on its own. Okay, so make sure you check that out. It's a good demonstration of exactly what the Coriolis effect is talking about. Okay, the next one is another video. This is the lab that we usually do. It's a video of the lab that we usually do, where we take a pencil and we put it between two pieces of paper representing the globe, and we spin the globe around and we put droplets of water, and you can see how the water travels on Earth, and you'll notice that it doesn't spin or it doesn't travel in a straight line because of Earth's rotation. Okay, so Coriolis effect. Okay, the object's motion is what we call u. It's in meters per second, and that is the object's velocity. The Earth's rotational motion is L times F, which is the path length. F is the Earth's rotational frequency, so exactly like how fast it is rotating. And we described the Coriolis effect using a Rossby number, which is called RO, or just rho for short. So the motion of the object divided by the motion of the Earth describes this Coriolis effect. Okay, when we have a small rho number, that means the Coriolis effect is very, very important for that object. Okay, when it's really, really big, that thing is not affected that much. Okay, but when the numbers are really, really low, that means that the curve is very, very apparent and very easy to see. Okay, so what I'm trying to get at there is like, and we'll see here in a little bit some of these different rho numbers. By no means am I going to have you guys do calculations on this. That's a little bit outside the realm of this class. But What I do want you to know is that when rho numbers are small, things are greatly affected by the Coriolis effect and by Earth's rotation. When the rho numbers are really big, they are not affected by Earth's rotation. Okay, here are some examples. As you can tell, I have the rho numbers over here on the right. So for example, a hurricane moves at 32 meters per second, the L value being 400,000. And when you calculate all of this, you get 0.8. That is a relatively low rho number, meaning that hurricanes are definitely affected by the Coriolis effect, meaning they don't travel in straight lines, even though they technically should. Okay, but because of the curvature of, or because of the rotation of the Earth, they follow more of a curved pattern rather than a straight line. Okay, other things that have high rho values, the bullet of a gun, not affected that much by the Coriolis effect. Toilets, okay, when you flush a toilet and it spins around, 20,000, not affected by the Coriolis effect that much. Okay, you'll see other low values like jet streams, which is a wind source, greatly affected by the Coriolis effect. Ocean currents, look how low ocean currents are. They are so low that they are the thing that matter, or that are influenced the most by Coriolis effect. Airplanes, slightly. Railway gun, not that much either. Okay, anything that is close to like 1, okay, 2, kind of, but anything below 1 is definitely affected by the Coriolis effect. Okay, so relating that back to what we're talking about, ocean currents. Okay, Coriolis effect. It explains why objects moving in a straight line appear to curve. Okay, so we send it out this way, straight at you, but what you witness as we're rotating is that it veers off one way or the other. And so what we see with currents is that that also happens. As the Earth spins, okay, these currents that normally would travel in straight lines if we were perfectly stationary are going to curve. Okay, this is only important on large scales like our ocean currents. Okay, so it doesn't affect lakes or rivers or stuff like that. Only our major water systems does this affect. Hey, it helps us understand wind, and we're going to be talking next video about certain wind habit, or things about how the wind affects climate as well. And it definitely affects water currents, which is why we're talking about it now. Okay, again, there's 2 more videos I want you to watch. Each of them are roughly around 6 minutes. They give you even more information on Coriolis effects, and they can do much better visuals than I can get you right now. Usually we watch these as a class and we talk about them, but make sure that you check them out. They do a great job of showing you what happens to the water as it's going through the Coriolis effect and what that kind of looks like. Okay, one thing that also we need to talk about are Ekman spirals. So Ekman was a scientist. He had a ship in the North Pole, and what he did is he observed that icebergs did not move in the direction that the wind was pushing them. Okay, so he figured these icebergs are sitting in the water. It would make sense that if the winds are pushing north, why are the icebergs traveling at 45-degree angles to the wind? Okay, that didn't make sense to him, so he was trying to figure out exactly why that was happening, because you would imagine something that's just floating in water, whatever way the wind is blowing, you would imagine that it would flow that way. Okay, and so that's what we're set out to kind of figure out with Ekman spirals. Okay, so wind and the Coriolis effect compete for this water movement. So if you imagine the iceberg is not going to move with the wind because it's actually going to move with the water. And so what ends up happening is we create this spiral, because what happens is the wind is pushing on the surface water, and then because of cohesion, one of those properties that we talked about how water likes to connect to itself, the surface water pushes on the water below it, and then that water pushes on the water below it, and then that water pushes on the water below it, and so on and so forth all the way down. Okay, now, based on the strength of the wind, okay, this spiral can go on for several meters in depth. If it's very weak, it may not go that deep. And then Coriolis effect deflects water deeper down to be traveling not in these straight lines, but they kind of just follow after the force of the wind is dissipated all the way through the water. It travels in the direction that was last, the force was last applied, if that makes sense. Okay, and so what we observe is that when the wind blows, the icebergs tended to travel at 45-degree angles to the wind because of this effect right here, the Ekman spiral. Okay, the wind may be blowing this way, but because of the Coriolis effect's curvature, the surface water is actually going to be traveling at near a 45-degree angle. And then if you imagine the layer below that, I'm going to highlight it here, is going to be at another 45-degree angle. And then this water is going to be at another 45-degree angle. And again, until all of that energy, all of that force from the wind is dissipated through the water, that will continue down. Let's see if I can get my pen. Okay, so Ekman spirals and current. So basically this wind and this current together kind of help the flow of all the water. Okay, we'll talk again about different winds and what they do in our next, I believe our next video, talk about trade winds and certain winds that blow east to west and west to east and stuff like that. But this combination of the Coriolis effect and Ekman spirals kind of tell you where the most water is being transported and how it's being transported. You can kind of see on this picture in the bottom left where the winds are blowing and then how the water is traveling in this circle. Okay, it goes with it, and it doesn't travel again in a straight line because of the Coriolis effect, so it gets this curvature, which ends up being really important because what happens is that it carries nutrients and it also carries weather with it. Remember, our unit is about climate. Okay, so all this stuff is being brought from other places and affecting the climate in different regions. Okay, so okay, my image is blocking my words, but it says, okay, so what does this mean? Okay, so the wind pushes the water. Okay, so wind puts stress on the surface water. Basically, what's going to happen is that surface water is going to get pushed away, and it's got to be replenished by something. And so this is where upwelling that I talked about in my last video happens. Upwelling, if you remember, is where the nutrients and the really, really dense salty water below the surface water, the deep ocean water, comes up to the surface. So when the wind comes off of the shore, okay, and pushes the water out, the deep salty water comes in and it provides more nutrients to that area. So deep cold water rises towards the surface, usually due to surface winds pushing the water away, and this brings nutrients up from the ocean floor for vegetation and other things to feed on, and then that again affects the wildlife, affects the climate, affects everything in that ecosystem. Okay, this only occurs on coastal areas that have deep drop-offs. Okay, if it has a really, really slow kind of beach to ocean, this typically doesn't happen that much. we're looking specifically for places where you go out, there's beach, and then just probably a few feet, maybe not a few feet, but a little bit longer than a few feet, and then there is a steep drop off not too far from land. Okay, so this is the video of upwelling that I was telling you about. Usually I do this as a demonstration, but instead we have to settle for this video where you're going to see this blue water represents the nutrients that are on the ocean floor, the really, really salty water down there, and all the nutrients, and it'll show you how that gets brought back up, because this thing in the top left is a fan and it's blowing the surface water. And by blowing the surface water, it forms this spiral where the upwelling can occur. Okay, there's another video on upwelling off the Oregon coast that I would like you to watch as well. It kind of catches it on what it looks like in real life, not just in Tupperware piece of plastic. And so hopefully this will give you even more idea of like how that works in real life. All right, so overall, for ocean currents, the things that you need to know. Okay, last time we talked about thermohaline, thermohaline currents, about how salt and temperature affect the density, and that powers some of the circulation of our currents, and how some places can be warmer than others because of where they are at in the current. The Coriolis effect, based on the spinning of the Earth, curves these currents so that they don't travel in straight lines. Surface air push the water into an Ekman spiral, so the surface water gets pushed at a 45-degree angle. Everything below gets 45-degree angle, 45-degree angle, and this is what causes upwelling and that spiral to bring up those nutrients from the ocean floor. Okay. And that is all I have for you, other than this last video. It kind of sums up ocean currents for you. Let me know if you have any questions. Let me know if you need any help. Make sure that you guys are staying on top of your stuff. We only have about a month left of school until the final, and then we are to the summer and done with online learning, and hopefully all this passes and we can be back to school in August like normal. But until then, thanks for watching. Let me know if you need anything.